Hello and welcome. Today, we're going to tackle a problem that pretty much every data scientist runs into. You've got a really critical question, you've got a bunch of different models, but you can only pick one to be the right choice. We're going to use a real-world diabetes data set to walk you through exactly how to go from just a basic first guess to a finely tuned, totally trustworthy prediction. And really, this question is at the heart of the whole thing. We're not just playing around with algorithms here. We're choosing a tool that could have a real impact on someone's health. So how do we build a model that gives us a prediction we can actually trust and, maybe more importantly, act on? For this particular challenge, we have a very clear, non-negotiable goal. We absolutely must correctly identify at least 80% of the patients who actually have diabetes. This is our recall target. What that means is we're prioritizing finding as many true cases as we possibly can, even if it means we get a few false alarms along the way. And this one number, it's going to guide every single decision we make from here on out. So let's set the scene. What's the actual clinical challenge we're facing? We're using a famous data set to try and build a model that can flag patients who are at risk for diabetes. The whole point is early detection, right? Because that can make a massive difference in how things turn out for the patient. The data set itself gives us a snapshot of 768 patients, and for each one, we have 8 different health metrics, things like glucose, BMI, and age. About 35% of them are diabetic. But here's the kicker, and this is so important. In this scenario, missing a positive case, what we call a false negative, is way, way more dangerous than a false alarm. A misdiagnosis could lead to serious problems down the road, and that one fact is going to shape our entire strategy. All right, let's bring in our contenders. We're going to start by just testing 3 common models straight out of the box. No special tuning, no fancy tricks. This is just to get a baseline to see what's possible from the get-go. And here we go, our first results. Okay, so logistic regression is the most precise. That means when it predicts someone has diabetes, it's usually correct. It also has the highest AUC, which is just a general measure of how well it can tell the two groups apart. But look at that recall column. Naive Bayes is catching almost 70% of the diabetic patients. That's the highest of the 3. And boom, right away we've hit our first classic trade-off. Do we want the most accurate predictions, or do we want to find the most sick people? Okay, those first results are a decent start, but we know we can do better. So now, we're going to roll up our sleeves and focus on just one of these models, the decision tree, and really get into the craft of tuning. This is where we can unlock a model's true power. So what is a decision tree anyway? You know, the easiest way to picture it is it's just a flowchart. Seriously. It just asks a series of simple if-then questions about a patient's data, like, is their glucose over 140, and follows the path down to a final prediction. It's simple, it's visual, and it's surprisingly powerful. Our first tuning knob controls the size of the final groups, or leaves, and this is a big one, because think about it. You don't want your model creating a major rule based on what it saw from just 1 or 2 people, right? That's not a stable or reliable pattern. So for our data set, we're going to say any final group has to have at least 8 to 15 patients in it. That makes sure the rules it learns are actually meaningful. Next up, we can tell the model, hey, don't even bother trying to split a group if it's already pretty small. You can think of this as a kind of gatekeeper. If we have a group with fewer than, say, 20 people, we just stop there. This keeps the tree from getting way too complex and creating rules that only apply to a tiny handful of individuals. This one's pretty straightforward. We just put a hard limit on how many if-then questions it can ask in a row. For medical data, we usually like shallower trees, maybe 3 to 6 levels deep. This does 2 things. It keeps the rules simple enough for a doctor to actually understand, and it stops the model from basically memorizing the training data instead of learning the real general patterns. And finally, we can tell the tree to just chill out and stop splitting if a group is already very pure, like if 95% of the patients in that little group are non-diabetic. It's really just a common sense setting that stops the model from wasting its time trying to perfectly classify every last outlier. So, what's the payoff for all this work? Well, now we can create different personalities for our tree. If we need super simple, clean rules for a clinician to review, we use the interpretable settings. If we need a good mix of precision and recall, we go for balanced. And if our number one priority is catching every possible case, we dial in the recall-friendly settings. This just shows how tuning lets us shape the model's behavior to fit exactly what we need. All right, so we've figured out how to tune one single tree. That's cool, but what if we could combine the wisdom of, say, hundreds of slightly different trees? That's the idea behind our next model. where we scale things up to build something way more powerful. A single, well-tuned decision tree is awesome. It gives you those clear, explainable rules we were talking about, which is fantastic for transparency. But the weakness of a single tree is that it can be a little unstable. Small changes in the data can sometimes lead to a totally different set of rules. So what's the solution? Yeah, you build a whole forest of them. By getting each tree to look at the problem from a slightly different angle, the combined result, the wisdom of the crowd, ends up being way more accurate and a lot more stable. This is the whole idea behind the random forest model. So how do we actually build one of these things? Well, it's all about setting up the recipe. First, you decide on the number of trees. Think of this as the size of our expert committee. Let's say 300. Now here's the secret sauce, the parameter that really makes a random forest work its magic. It's called mtry. This little setting is what injects the randomness into the forest. See, at every single decision point, instead of letting a tree look at all 8 of our health metrics, we force it to only consider a small, random handful. In our case, just 3. Why do we do this? It's genius, actually. It forces each tree to become a specialist in different patterns, creating this incredible diversity of opinion in our committee. And of course, we still use our other tuning rules like minimum group size to keep the individual trees from getting too crazy. The final prediction? It's just a simple vote from all 300 trees. Okay, the moment of truth. We've tuned our tree, we've built our forest. Let's bring everybody back for the final showdown and see which one is really the right tool for this job. Let's check out the final results. Now I've added a new column here, MCC. You can think of this as a sort of overall balance score. It's really good at telling you which model does the best all-around job when you have an unequal number of cases, like we do here. And who comes out on top? Look at that. Our random forest. While naive Bayes still technically has the highest recall, the random forest delivers the best, most balanced performance overall. And this really gets to the key lesson of this whole thing. The best model completely depends on what your goal is. If your one and only mission is raw screening power to catch the absolute maximum number of potential diabetics for follow-up, then yeah, naive Bayes is your champion. But if what you need is a strong, reliable, and balanced model for general purpose use, then the random forest performance is tough to argue with. So let's break this down into a super practical guide. Think of it like this. If you need maximum recall for a wide screening program, you pick naive Bayes. If you need a balanced, solid, all-around performer, you go with random forest. If you absolutely have to minimize false alarms before you order expensive tests, logistic regression is your best bet. And if the doctors demand simple, human-readable rules they can understand, well, that's the perfect job for our tuned decision tree. So I'll leave you with this question. You've seen the data. You understand the trade-offs. For this clinic, what would you choose? Would you go for the simple, explainable rules of the decision tree or the powerful, balanced performance of the random forest? There's no single right answer here. It all comes down to what you and the clinic value most. Thanks for watching.